So in this, the final section of mathematics in this module, we're going to use what we've learned about continuous time Markov jump processes to look at two useful models for real-life applications. And these are models in the area of what mathematically we call queues, although in fact, only the second one of these will actually involve queuing up to wait. And in the first, we won't be queuing in the English language sense. The idea is, let's say I'm running a website that shows live streams of some pandas in a zoo. And what will happen is people will log on to the website to view my live stream of pandas at the zoo, and then after a while they'll get bored with watching it and they'll log off and leave the website. And so I might want to keep track of how many people are currently on my website watching my live stream of the pandas. If you don't want to think of this as people watching a live stream of pandas in a zoo, you could think of the number of students in the university library, or the number of contracts held by a broker, or the number of files being downloaded from an internet server. These are things where people arrive at some rates, and as owner of the Panda website, I probably know at what rate they arrive, let's call it lambda. And then they'll watch the live stream, or stay in the library, or hold the insurance contract for some random amount of time. And I probably, for experience, know what the average amount of time is. We could call it 1 over mu. And so I want to keep track of how many people are watching the live stream. In the long run, how many people on average are watching it? In the long run, what proportion of time is nobody watching it? For example, for what proportion of time is the library empty, or are no files being downloaded from the server? Those are all questions we might be interested in knowing. And note that in this example we're looking at here, as soon as the individual arrives, they start to receive the service. That is, as soon as they log onto my website, they start to view the live stream of the pandas in the zoo. So there's no actual queuing here. We'll come to that in the second example. But the first thing we're going to want to do is write this down as a Markov jump process. That is, we're going to want to write down the generator matrix Q, or at least the non-zero arrival and departure rates. So let's start by thinking more about this process of my live stream of pandas in the zoo as a continuous time Markov jump process. Okay, so let's try to look at what's going on with this process. So what we can do is we can let xt be the number of individuals in the process at time t. When I say in the process, I mean they're receiving the service, as in they are logged on to my Panda website. So, receiving service at time t. So we said that arrivals happen like a Poisson process of rate lambda, because that's the model that we know for arrivals happening. And so when someone logs into my website, they then watch the pandas, that is, they receive the service for an exponential mu amount of time. So that is, they watch my pandas for an average of time 1 over mu, which is the expectation of an expected mu amount of time. Okay, so what are the transition rates? What's our matrix Q going to look like? Well, the arrivals tells us that we go up from I to I plus 1 at rate lambda. That's precisely what the Poisson process arrivals means. What about departures? So the departures will happen at rate qi minus 1. So when we have I people receiving the service, we have I people watching my panda cam, then it will go down when the first one of those I people log off. By the memoryless property of the exponential distribution, they've all got an exponential mu time left. And so the minimum of those I exponential mu times is exponential I mu. Right? That's a result we saw back in, I don't know, when we were doing the Poisson process. Right? The minimum of all those exponential mu times is exponential I mu. Those are the only non-zero transitions, but remember, of course, that because rows of the matrix add up to 0, we must have that qii equals minus lambda plus I mu to make sure the rows adds up to 0. And minus that we sometimes called qi. I'm not sure if we'll need qi later, but let me write it down just in case we do. So to write down a picture of what this looks like, we've got 0 people watching the panda cam, 2 people watching, 3 people watching, 4, and so on. And transitions upwards are happening when someone arrives, which happens with probability lambda. And departures happen with probability I times mu. So that one's mu, that one's 2 mu, that one's 3 mu, that one's 4 mu, etc. So this is kind of forcing the process down. It means I'm probably not going to get like billions and billions of people watching my panda cam, because when there's lots and lots of people watching it, that means departures are going to happen very quickly. So it has this kind of self-fixing idea. So as you might have seen from the title of this section, this is often called an MM infinity queue or an MM infinity process. So here, let me explain what these letters stand for. This is a kind of a standard notation that queuing theorists use. The first letter tells you about what happens with the arrivals. So this means memoryless arrivals. Some people say the M stands for Markovian, because Markov property means memoryless. So memoryless arrivals means the inter-arrival times are exponentially distributed. That's the distribution with the memoryless property, which means that arrivals are like a Poisson process. Memoryless arrivals means arrivals like a Poisson process. The second letter tells queuing theorists what the service time behaves like. So again, this M again stands for memoryless or Markovian. And so we have here memoryless service times, which means they must be exponentially distributed, because it's the exponential distribution that has the memoryless property. And then this third character stands for how many servers. So here we had infinite servers, by which I mean that there's no limit to how many people can receive service at a time. There's no limit to how many people log onto my website to watch the webcam of the pandas. No limit on number of people receiving service. In the next subsection, we'll look at a case where there is a limit on the number of people who can receive service. So there's lots of various generalizations of this, like a queuing theorist will know what you mean if you say, I've got an MGS infinity queue or something. But so just to let you know, this one is called the M infinity. So what might we want to know about this MM infinity process? Well, we might want to know, in the long run, how many individuals are being serviced. That is, in the long run, what's the average number of people watching my webcam of the pandas? We also might want to know, in the long run, for what proportion of time is no one being serviced? Because if we're modelling this as people in the library, if there's no one in the library, then the librarian can go home and we can lock the doors. So we might be interested for what proportion of time there's no one being serviced. So for questions about the long run proportion of time, as we know in this course, what we have to do, we have to find the stationary distribution, and then we can apply convergence to equilibrium or the ergodic theorem or whatever. So if we want to know useful things about this process, like what happens in the long run, we need to find the stationary distribution. So you'll remember that a stationary distribution solves pi q equals 0, or to write it out in coordinate form, sum of pi I qij equals 0. So note that that sum there is about all the entries going into state J. I'm actually going to swap letters and use states going into I. So we can jump down to I from Qi plus 1, right? So that will give us a pi I plus 1 times the probability of going down, which was I plus 1 mu is the probability we go down from I plus 1. We could stay where we are because that diagonal entry of the matrix is negative. We said the diagonal entry was minus lambda plus I mu pi I. Or we could move up from I minus 1, and that happens with rate lambda, that we move up from I minus 1. We want that to be equal to 0. So that's the equation we have to solve to find a stationary distribution. It turns out that that's not actually a very easy equation to solve, like using standard techniques, because of this I hanging around. It's not like a linear difference equation or anything. So the best tactic here is to try and guess what the answer is. And I won't go through the details here, but if you calculate what pi 1 is in terms of pi 0, you find out that pi 1 equals rho pi 0. Feel free just to put in I equals 1 and check it out. Similarly, if you try it out, you'll find that pi 2 in terms of pi 0 is rho squared over 2 pi 0, and that pi 3 equals rho cubed over 6 pi 0, where here rho is lambda over mu. That's kind of the ratio of the rate at which people arrive to the rate at which people leave. So I looked at the first few of those and I thought, I know what this looks suspiciously like. It looks like pi I equals pi 0 rho to the I over I factorial, which therefore must be e to the minus rho to the I over factorial, which is the Poisson-Rho distribution. That's what it looks like it's probably going to be. So let me check. So I need to check this, because my suspicion is that the Poisson distribution is going to be the stationary distribution. So to check it, you just have to substitute this thing here, into this equation and check that it really does equal to 0. If you want to see me check that, it's 5 lines of algebra in the notes. I'm not going to write it down here because it will be boring to watch it on video, but you can check that does in fact work and really is the stationary distribution. So the stationary distribution is this Poisson distribution with rate rho equals lambda over mu. So we're irreducible, we're positive recurrent, so this is an equilibrium distribution. We have an ergodic theorem on the long run amount of time. So what's the average number of people in the long run in my process? Well, it's precisely the expected value of this Poisson-Rho distribution, isn't it? And that's rho. The expected value of Poisson-Rho is rho, which is lambda over mu. So the average number of people is watching my panda cam is the same as the ratio of the rate of arrivals to how long people spend in there. That's kind of not surprising somehow. It kind of feels like the right answer. So the average number of people in the process, the average number of viewers, and the proportion of time that all the servers are idle because nobody's watching the panda cam. Well, by the ergodic theorem, that's just pi 0, isn't it? The amount of time spent in state 0, and for the Poisson distribution, that's e to the minus rho, which is e to the minus lambda over mu. So that tells you what proportion of time all our servers aren't letting anybody, well, there's nobody who wants to watch my panda cam. Okay, so that's all I have to say really about this MM-infinity process. In the next section, we'll look at a different process that does have a limit on the number of servers.